Hello everyone, my name is Shubh Bhattacharya and I'm here to present my work on recognition of complex event in open source web scale. When here are provided some specific examples, taking the three different conditions, what the party for humans, these are relatively easier to detect than they are because of the several problems in implementation, such as environmental background program and some changes. These are hard problems in computer vision and across multiple communities. Other than that, they are very diverse, but they participate in the role as well as experience and they can be referred to a Python, Word, or PHP. So these are much more challenging problems. Why would you want to do that? The motivation comes from three different aspects. One is if we can solve this problem, we can do efficient summarization for analytical purposes. We can also do virality prediction. Given a video, you can actually predict whether it is viral or not based on its content. And also it can be used for production-related techniques. Now, what have been the earlier approaches to solve this problem? Mostly divided into two parts. First one being low-level feature-based, where you extract features, perform vector quantization, and feed that to a low-level event classifier. It is relatively easy to understand and implement and gives decent recognition performance, but the problem has its own little semantic interpretation. There's another approach that has been looked into this for some time now, which is a concept-based approach where each video is divided into a set of concepts, and the concepts there are concept-based detectors which apply on video, and you get a concept-based representation. This can be used to a final event-based classifier, and although it's relatively more complex and has a good semantic interpretation, it has a lot of room for improvement, and which is why our talk is going to focus on this part. Now, let's look at how we define the concepts. Now, at the lowest level, we have attributes such as right arm moving up, left arm moving up, so on and so forth, which comprise the actions such as person waving hands or running. When a particular human actually interacts with an object, then what we call it is an interaction such as person blowing candles, and together each action and interaction form the concept. Now, if we take the interaction between the concepts, such as the temporal relationship between the concepts, what we get is the complex event, which is now here we are showing an example of changing a tire. Now, as we go up the hierarchy, the complexity increases, and our goal is to divide this complex recognition problem into these different tiers so that we can solve the problem efficiently. Now, here is the summary of the bottom-up approach, where we are contributing at the lowest level, which is design of novel features. We are also contributing a computationally efficient intermediate representation for explaining the concepts. And then the third one is exploiting the temporal and dynamic correlation. Now, the lowest level, where we are talking about the novel features, we have proposed two different features. One is a fast semi-global short-level descriptor based on covariance matrices, and it can be used for a variety of purposes such as gesture recognition and action recognition. Second one is a novel camera motion descriptor, which is based on Lie algebra projective groups, and it can be used for shot classification and complex recognition. The covariance descriptor is computed as follows: intensity RGB values, then differential intensities, which is the gradients, and then we also have the motion-related information, optical flow, derivative of optical flow, divergence, vorticity, and so on and so forth. So, a given clip can be described in terms of this covariance matrix descriptor. The good part is we don't need any kind of spatiotemporal feature detection for this purpose. So here is the idea of the approach. First, we have a video divided into clips, compute low-level features, compute the covariance matrices from those features, and then Here are some details on what the covariance matrix features looks like, and we can actually leverage classification strategies specifically for matrices. One example is given here, which works pretty well. Based on TensorSpark coding. I won't go into much details here. So bottom chart actually shows how we come up with this novel optimization problem to solve this sparse coding using matrices. Here are some results on KTH actions, UCF 50 and human motion database 51. As you can see, our method outperforms the bag of words on the state-of-the-art spatiotemporal feature detectors. Also did some experiments on one-shot gesture recognition, and here are some results. Those are bag of words based methods and template matching, and these are our methods, and as you can see, we comfortably beat the state of the art. Now, moving on to the next topic, which is representing the camera motion. We have come up with this new technique which eliminates the use of full structure from motion recovery to estimate the camera position. Our technique is based on homographies, where we only compute homographies across consecutive pair of frames, and we estimate the camera motion. The way we do it is, as you can see here, different short homographies which are indicated in the inset, and those are the elements which are more discriminative in the homography. Now, the good part is, although we have this discrimination, but that is in the projective space, we want to transform it to a linear space, which we do using Lie algebra or projective groups. And here are the details given here. Our motion representation is the alpha, which is basically the coefficient of the Lie bases. And here is a block diagram that shows how we do this. Given a sequence, we compute in the frame homography, project them using Lie bases, and get a vector space mapping, which is an 8-dimensional vector time series. On the time series, we expect feet and give it to classifier. Now, here are some experimental results on our own 8-class short data set. These are some statistics, and the red bar actually shows our proposed performance. Brown bar is the structure from motion based performance, and as you can see, we are very close to that. But the good part is our time consumption is much less than the full structure from motion. Some complex event recognition on the set with multimedia event detection challenge 2011. 15 events. The top chart actually shows events that have very little camera motion, and the one that on the down shows events with more camera motion. And you can see our approach does comparably better than the art. Moving on to the next topic, which is computationally efficient, meaningful internal representation. So here we propose an approach which is alternative to the traditional bag of words. We describe each instance as an unknown distribution of a set of representative data points. These data points we are selecting not by clustering, but just random sampling. Now, our idea is to find the optimal combination of weights across all these selective data points, which we call anchors. Now, we solved this using a maximum likelihood based approach, and this is a combinatorial problem. So we use bounded optimization technique to solve this. More details can be found in our CVPR 2011 paper. I'm going to show you a simulated examples where C1, C2, C3 are our anchors, and the D1 and D2 are data points. These are the distances between them. Standard bag of words representation would look like this. Assignment, which is proposed by Van Giemert et al., would also look like this. And our proposed implementation, since it's an iterative technique, it would tend to weigh those anchors which have higher memberships to different data points more. And that's how the lowest chart would actually be the representation after conversion. We also did some action recognition experiments on KTH dataset and the UCF11 dataset, and these are our performance. The chart at the bottom actually shows how the selection of different number of anchors affect. Also, we did some experiments on spatiotemporal action concept detections. This is specifically targeted for the TrackVid Med 11 dataset. where we have identified 93 spatiotemporal action concepts. Some samples are given here as person eating, person falling, and we use our representations to detect these actions. And our representations can work on any features, so we test with different modalities. And here are the average precisions for different concepts for all the concepts. Now, interesting to note that our representation gives 2.5% better results than the before. Now, moving on to the next topic, which is temporal representations between temporal relationships between these action concepts. So here we show an example. We divide a video into different clips and apply concept detectors on these clips. We get a linear dynamical system which looks like this, where each of the time steps are basically a vector represented by the detected responses. Now, these CDFs of these concept detectors can give a good of how the events looks like. So we formulate this concept-based dynamical system, linear dynamical system for modeling the relationship between these different concepts. Now, we use a Hinkel matrix-based descriptor to extract important features from these temporally evolving series. And also, we do some temporal signatures using parsimonious linear fingerprinting, which actually captures sinusoidal and exponential growth properties from these time series. Some results on the Med11 data. Here are some conclusions. First, we extracted two different complementary features from videos based on covariance matrix and camera motion. Then we also showed a maximum likelihood-based intermediate representation. And third one, we extracted temporal dynamics in a very meaningful way. Now, here are some relevant publications, and myself in the center, and my advisor, Professor Shah, and Doctoral are the left and right. And thank you very much.